recording. Hello everyone, this is the second part of the lesson for chapter 4.2, maximum and minimum values. And notice that the last question, we kind of looked at a nice sketch to find our local maximum and our local minimum and our absolute minimum. But we don't always need to read them off of a graph. Without sketching, we can find the local maximums and local minimum values. Before I go any further, too, if you're right now sketching this diagram and you look back at your notes later and say, I didn't do a great job of sketching that diagram, I hope you do know that you can actually go through to your OneNote file through Teams, and I've shared this notes file with you, so you can actually just get these diagrams. So if you look for that, you should be able to find it. Okay, anyway, without sketching, we can find the local maximum and minimums. How? Well, we know that anywhere that you have a local, let me get off of highlighter. Anywhere that you have a local maximum and a local minimum, of course, you have a peak. And peaks have slopes of 0 or derivatives equal to 0. Okay? Except notice that this one is a little different. I mean, very obviously that is a local maximum. In fact, looking at this graph, assuming that goes down forever and that curves away forever, which I guess we don't really know, but assuming that, then it would be an absolute maximum. But what do we know about that one? Remember how this works? What do we know? How come they didn't put a little red line here like they did for the other ones? Does anybody remember that from way back earlier in the course? Feel free to turn on your mic and tell me what you're thinking, or answer in the chat. How come they didn't put the little red line there? I'll give you a hint. Remember we called those points cusps? What do you know about a cusp? Uh-oh. I can feel your blank stares through the screen. Nobody remembers this from earlier in the course? What's special about that one? How come they didn't put a little red line there?
Is it indifferentiable?
Very good. Oh, nice use of the terminology, too. That is exactly true. You can't find the derivative at that point. It is not differentiable because there isn't really a single tangent to a cusp, right? There is only one tangent line right there that meets that point, and it's going to have a slope of 0. I could give you infinite tangents to that point that would only touch that point at one place, but only one of them would actually have a slope of 0, but you actually can't find the derivative of that point. So that gives us something that we call Fermat's theorem. Now you're probably going, hey, I remember that. This is Fermat's last theorem? No, Fermat's last theorem was a puzzle that had to do with exponents and Diophantine equations that took hundreds of years to solve. This is more of a rule that we can use that says if f, some function, has a local maximum or minimum, I hope you're okay with me just abbreviating those words, at, we'll call it c, value c, that's a lowercase c, then either f primed of c is equal to 0, or f primed of c does not exist. And as you can see, there's the two cases we have, right? The red lines, and I'll put these as red dots, that's this. My blue dot here, well, that's going to be where a derivative wouldn't even exist. Okay? And just make sure I do this right here. A critical value, and actually the book actually uses the term critical, and then I spell it wrong. The book uses the term critical number. Critical value, critical number, doesn't really matter, same thing. The critical value, or a critical value, I actually prefer critical number. Of a function. And this kind of defines what I mean by this letter C. What do we call that C? We don't just call it C, do we? No, we call it a critical number. So a critical number of a function is a number, and we usually use C, it doesn't really matter, in the domain of the function such that either, and this basically says the same thing as Fermat's theorem, f primed of C equals 0, or f primed of C does not exist. And if I ask you, hey, what's the critical number here? Well, I'd say, well, that critical number is A. That critical number is B. So maybe this is 1. Maybe this is 3. Maybe this one's 7. Those are the critical numbers. Maybe this one's 8, right? This critical number here, again. Tell me about point D. I kind of forgot about it. Would it be red or would it be blue? It would be blue. That's a cusp. Those are all critical numbers, what the X values are. If you ask what's a critical point, of course, if I ask you for a critical number, you just tell me what X is. But if the work asks you for what's the critical point, well, then I actually want to know what the Y value is too, and I want an actual coordinate point, right? If somebody asks you for a point, they're asking you for an X coordinate and a Y coordinate. But if I just say, give me the value, they're asking for the X value, okay? So there we go. So there's a couple of definitions for today. And then I thought we'd hit an example here and do this as like a big sort of grade 12 plus calculus problem. So again, I know some of you, probably the majority of you, are either doing 40S pre-cal right now, in which case you've done this unit, or you have it next semester. So you haven't really done much. At the beginning of this course, we did a little mini unit where we kind of reviewed some grade 11 and 12 algebra, where we saw a couple of these things. We actually called it, I think it was called the factor theorem on that worksheet from review of old material. So we're going to just use that, and I'm actually going to add to this question. I'm going to say find the absolute, and I'm going to say and local maximums and minimums. Oh, and actually I realized this morning that I kind of forgot yesterday. Local maximum minimum is what most textbooks call it, but sometimes they're also called relative. The relative maximum and the relative minimum. And I think that just means relative to where I am and the region that I'm in on the graph. Move that a little bit. There we go. Okay, so find the absolute maximum and the absolute minimum and the local maximum and local minimum values of this function. Now, we're going to use Desmos to help us with this sometimes, but sometimes we can do this pretty much Desmos free. Assuming that the function that I'm working with is factorable. So is that factorable? Well, we don't really know how to factor cubes. I actually can't show you. There is, just like there's a quadratic equation for when you hit a quadratic that you can't factor, there actually is an equation for factoring cubes. And I looked it up the other day, and we could break it out if we wanted to, but it's not pretty. Oops, hang on. How do I get to bookmarks? There's my bookmarks. Way down here. Yeah, there it is. There's the cubic formula. How would you like? There's the quadratic formula, of course, our old favorite, the old standby. Check out the cubic formula. That doesn't look like much fun. That is a nasty piece of work. But of course, keep in mind that a computer, if you took the time to program that into a computer, to a spreadsheet, whatever, it would be a lot of work, but once you've done it, you've got it, right? You could just enter numbers into, and the computer spits out the formula. What would take you a half an hour of computing and calculating, computers can do, practically instantaneously. And by the way, this formula was actually discovered in the 1500s, the 16th century. And in those days, mathematicians used to kind of, in a weird way, have duels. It was almost like a sport, right? They'd throw a problem at them, and two guys would go, and whoever the better mathematician was would solve it first. So Cardano, the actual mathematician who came up with this, kept it to himself until very late in his life when he finally started sharing it with colleagues, because he liked the idea that he could use this to smoke his opponents at battles, which I always kind of found interesting. Luckily, math isn't like that anymore. Although maybe, I don't know, maybe it'd be fun. We do write math contests, don't we? Wouldn't it be cool if instead we did duels? Math duels. There could be a place for that. Anyway, so we're going to not try to solve these things if they don't factor. We're going to use Desmos to help us. But before we jump and go run into Desmos, are we sure this doesn't factor? And the grade 12 way to factor this is to look at the 2 and go, if this has integer factors, then the factors of 2 would make this thing 0 when you plug them in for x. So I'm going to try finding, well, first of all, what's f of 1? Would that make 0? And I can tell right away, no, they're all positive, so that would, no, that's not going to make 0. Does f of negative 1 work? And I've already done the work here, so I can tell you no, that it doesn't. But you know what? F of 2 does work. F of 2, or sorry, F of 2 work? I think I meant to say f of negative 2 works. Yeah, that's right. Obviously, a positive can't make any of this negative. But f of negative 2 works, because then I'd get x cubed, which is negative 8. Remember that the cube of a negative is still negative. And plus 6x squared, which is plus 24. And plus 9x, which is minus 18. And then plus 2. And as you can see there, if you add that up, you get 0. Right? Negative 8 plus 24 is 16. 16 minus 18 is negative 2. Negative 2 plus 2 is 0. So that means, therefore, x equals negative 2 is an x-intercept. I'll use the word 0. And x plus 2 is a factor. So that's the 2 things I can conclude. And we called that the factor theorem when we taught it in grade 12, and in this course when we kind of reviewed it really quick at the beginning of the course. And so that tells me then that I can figure out what the rest of the factors of this thing are by dividing, right? Hey, if I tell you, hey, I've got a number, like it's a great big number, it's the number 144, and you find out, oh, 16 is a factor. What's the other factor that goes with it? Well, I'll have to go 144 divided by 16. So I'm going to have to take that x plus 2 and divide it in to my function. And I'm going to do long division. And again, this is something else that we reviewed at the beginning of the course. You've done it if you've done the grade 12 course. X goes into x cubed, x squared times. And somebody usually asks me here, can I use synthetic division? Sure, go ahead. I'm not a fan of synthetic division. I prefer doing it the long way. So that's x cubed plus 2x squared, right, which is just this thing times those things. And then remember that you subtract, get a remainder, and bring down. Okay, how many x's go into 4x squared? 4x of them, giving me 4x squared plus 8x, and I'm subtracting that. That gives me, now this should have no remainder because after all I did divide by one of the factors. So plus 1, and there we go. So I actually know that f of x can be expressed as x plus 2 times x squared plus 4x plus 1. And this thing here unfortunately doesn't factor. So I'm going to have to back up, and I'm going to have to use my quadratic formula on that. So that'd be minus b plus or minus the square root of b squared. Oh wait, I already squared it. I don't want to square it again. B squared minus 4 times 1 AC all over 2a, which is, that's going to be negative 4 plus or minus 16 minus 4 is 12, so root of 12 over 2. Now I'm going to use my grade 10 and 11 radical skills to make this an easier number to work with. I can factor a 4 or a square root of 4 out of that radical, which would make this negative 4 plus or minus 2 root 3. And then I can divide both of those things by the 2. So my other x answers here, my other zeros are negative 2 plus or minus root 3. And okay. Suppose I was not allowed a calculator to do this, but I wanted some idea where those numbers are. I can, of course, then just sort of say that this is approximately equal to negative 2 plus or minus, the square root of 3 I know is around 1.7, good enough. So I have approximate zeros at, let's see, if I have negative 2 plus 1.7, that'd be negative 0.3. And if I have negative 2 minus 1.7, I have negative 2.7. So there's my zeros. My zeros happen at negative 2, negative 0.3, and negative 2.7. What else do I know about this thing? Oh, well, here's another thing that I can
It'd be
use to graph.
negative 3.7.
That's a negative 3.7. Thank you very much.
Yeah.
You're more awake than I am. Y-intercepts are easy to find, right? You just look at this. It's in standard form. If x is 0, I get 0 plus 0 plus 0 plus 2. So my y-intercept is 2. When you're in standard form, your constant is always your y-intercept. I think I'm ready to make a sketch of this thing. So let's sketch it. We have a pen that doesn't want to work for a second here. Let's see. Let's try that again. No. There we go. Okay, pen, come on. Don't let me down, pen. Okay, let's see. Let's get out of here. And then let's go back. And is that, yeah, there we go. That for some reason kicks my pen back into behaving itself when it freezes. I don't know why that is. Okay, anyway, there's my grid. And okay, so we have an x-intercept at negative 2, right? We have an x-intercept at negative 3.7. So there's negative 3, negative 4, so maybe there. And we have an x-intercept at negative 0.3, so that may be that. And then we have, that's it. There can't be any more x-intercepts than that. Why? Because it's x cubed. That's all the zeros it can have. Now I want to know how it behaves. Well, I know that x cubed graphs generally look like this, right? They start going down and end going up. The only way they wouldn't would be if their leading coefficient was negative. And again, this is something you talk about in grade 12. So I know this one goes down forever. This one goes up forever. Oh, and it hits at the y-intercept of 2. But I don't quite know what else is happening. So of course, I'm going to, and you learn this also in grade 12, I'm going to make an interval diagram, right? And I can take the intervals. Okay, well, first of all, there's one other thing I've kind of ignored here. What does this mean again? Oh yeah, that means I'm actually restricting the domain of this thing. So I only want to know about this equation between negative 3.5 and 1. So I'm going to go back and actually do that. I'm going to say, all right, so I'm restricting my domain. So you know what? This thing isn't even going to make it to here. It's going to stop there, right? So this part of the graph doesn't even really exist. Goodbye, right? And I guess that dot has to go goodbye, but oh, of course, that wipes out my whole line. So now I got to go back and put my line back. There we go. And now I'm kind of fairly sure that it's going to, do this, right? Or something like that. But I don't know exactly. I want to make sure that I know what direction things are going. So I make an interval diagram. Okay, so and I'm almost out of time here. I might have to continue this example later. I thought I picked an example I could get through, but I did not. So I'm going to make an interval diagram. So what are my intervals? Well, I have an interval between here and here. So, and then I have another interval between here and here. Oops, come on. Between here and here. And then I have an interval, I'm going to make this one really small, between here and here. And then everything after that point is, basically its own interval. So, from there to forever. So I want to know what's happening in all of those intervals. So let me declutter my diagram, and let's actually talk about the intervals. Okay, so my intervals are as follows. Interval diagram, or interval chart, whatever you want to call it. When I go between negative 3.7, where this thing has a 0, or in this case, negative 3.5, because that's where the graph ends, and the next interval dot there happens at negative 2, I want to know what my two factors. Now remember, I have this in factored form here, right? Where is it? There it is. In factored form, that is the equation, right? So I would like to find out what's happening with these two factors. So this factor here is x plus 2. And the other factor is x squared plus 4x plus 1. And then what happens for all of the function. So in this interval, give me a number between negative 3.5 and negative 2. How about negative 3? Negative 3 will make this, this thing here negative. It'll make this thing here negative, right, because it'll have 9 minus 12, negative. So a negative times a negative is positive. So I know that between here and here, I am on the positive side of 0 when I'm between negative 2 and 3.5, right? All right, next interval. What happens between negative 2 and my next one was it negative 0.3? Well, give me a number between negative 2 and negative 0.3. How about negative 1? Negative 1 makes this factor positive, and it makes this factor negative, and a positive times a negative is negative. So I know I go down here. Okay? Next. My next interval is this tiny little interval between, actually I guess it's not tiny now that I think about it, that's not an x-intercept, that's it, that's my last interval. So basically my next interval, I just kind of realized I explained that badly earlier. Everything this way is now an interval because there's no more x-intercepts to get in the way. So this now is what happens when x is greater than negative 0.3. So you know the easiest number to work with that's bigger than negative 0.3? How about 0? 0 plus 2 is positive, 0 plus 0 plus 1 is positive, and that's positive. So I have this right, I know it goes up and it stays going up forever. And you're probably thinking, man, I could have known that all these things were going up and down just by looking at where the dots were, but this is only a cubic. They get much more complicated than this. So believe it or not, we're going to now say to be continued, and we will finish this off on Friday's class. That's as far as we're going to get today. We didn't quite get through the rest of the example because now we have to do the calculus part, because now we're going to do the part that you couldn't do back in grade 12 and figure out how high this is and how low that is. And that, of course, then is my local and absolute maximums and minimums. So we'll pick it up there and maybe do one more example on Friday. Okay? So before you go running away, my apologies if I've made you a little late for band. I will run attendance. There we go. Download attendance list. Download attendance list. There we go. All right, away you go. Enjoy the rest of your day, guys. Thanks for being here. If anybody has any other homework questions and they're sticking around, I'll leave the team meeting open. Maybe I'll adjust homework online here since I didn't quite get as far today as I thought I would. And so again, if you want to stick around and get some help for tomorrow's quiz, if implicit differentiation is still giving you grief, you can stick around. Otherwise, I'm going to end the video here for the people who are watching this at home, and the video will continue tomorrow.